This is the problem-solving session of the last lecture in this whole course, in this lecture set of lecture 19 on first isomorphism theorem. I'll do there are only 5 questions at the end of the chapter, so I'll do 2 of them, give you a feel. The first one is concerned with the alternating group. Go back to chapter 12 on permutations to refresh your memory on the symmetric group. Symmetric group, permutation group, same thing, just 2 different labels. So the symmetric group's usually just written capital S with little n. The little n here, well, maybe here it's a little bit bigger, refers to the number of objects that you're permuting. Right? So the symmetric group, permutation group, is the set of all possible permutations of n objects, and there'll be n factorial of them. Okay? Well, in this first question you're asked to show that the alternating group, and what's that? That's the subset, in fact a subgroup, and soon we'll show it's a normal subgroup. It's the subgroup of all even permutations, and permutations can be divided evenly, equally, into 2 categories, 2 subsets, not necessarily subgroups. One of them is a subgroup, and that is the even permutations and the odd permutations. And what does that mean? Well, any permutation can be written as a sequence of transpositions. So it's having a bit of revision here of chapter 12, theory of chapter 12. Now, can you remember what a transposition is? It's a cycle, more technical terms, it's a cycle of length 2. Okay? I won't explain what a cycle is. Go back to lecture 12, chapter 12, and refresh your memory. Anyway, so if a permutation has an even number of transpositions, then that permutation is said to be even. Okay? And if the permutation has an odd number of transpositions, that permutation is said to be odd. Okay? And permutations are either even or odd. In fact, they're equal numbers. We proved that, I think. Right? So you're asked to show that the alternating group, that's the subset, in fact subgroup, of even permutations, that you're to show that it's not just a subgroup but a normal subgroup. Okay? And given that we're in the chapter 19 on the first isomorphism theorem, we will use that as part of this question, of course, because it's one of the questions of chapter 19. You should expect that. All right. So the question asks you to show this relation, which is of this form. Right? It's of the first isomorphism theorem form. Okay. So I will not prove that the alternating group A of n is a subgroup, because we already did that. We did that in lecture 12, chapter 12. So we need to show now that it's a normal subgroup. So how to do that? So in other words, now to prove that a group is normal, you remember you have to do this kind of thing. You have to show that for any member of your starting group, in this case it would be symmetric group, so for any member of it, call it X. So X inverse and any element belonging to the subgroup you're trying to show is normal. So in this case, alternating group AN. Okay. So this A is just little a here. It's just any element of this group, the alternating group. Okay. So X inverse AX belongs to this group, alternating group. So if we can show that, that's the proof that that A is a normal subgroup. Okay. Now, how to go about doing that? Well, there's a very powerful technique we talked about in chapter 12, which was theorem 41, and here I've written it out again to remind you. So if you're a bit rusty, go back and study chapter 12 again, especially on this part. Anyway, theorem 41 says it uses this n here, and what is n? So n of x is just any permutation in your symmetric group, right? Just a permutation, and n of x is defined to be, well, strictly speaking, it's the number of inverted pairs. What's that? Again, go back to chapter 12. What is an inverted pair? It'll take quite a while to explain, but we did it thoroughly in chapter 12. So n is the number of inverted pairs, but the number of inverted pairs is equal to the number of line crossings. Like if here are your n objects, and say they're labelled, they're ID'd with a unique integer, so object 1, object 2, object n. So lay them out in order, and then perform your permutation x on those n objects, and you get a new permutation. The order of these objects will then be different. And then, so say that's object 2, and here's object 2. So draw a line between them. So you draw a line between object 1 and object 1 in this lower line somewhere, and then a line between object 2 and object 2, and so on. So you then count the number of crossings, cross points. Oh, that's what, yeah. Cross points, line crossings, yeah, cross points. I think I preferred that term, cross points. That's sort of clear. So it's the number of cross points. Cross points. Okay, so like here, for example, you've got a cross point, or a line crossing, or an intersection, or whatever. Okay, so this n here is the number of cross points in that permutation, and so theorem 41 says this. Okay, so if you perform two permutations, x and y, now if we're going to be strict about the order, usually the right hand one goes first, so you apply permutation y first, and then x. Okay, so the resulting permutation xy, whatever it is, the number of cross points it has, n of xy, will be this. Well, strictly speaking, minus 1 to the power of this is equal to this. So n of xy, nx plus ny as powers of minus 1. Right? So go back, refresh yourself about this, the theorem 41, because it's a very useful technique, and we will use it now to help prove that the alternating group is normal. It's a normal subgroup, right? So let's use this now, and so this is what we need to show, right? We need to show that x inverse little a x belongs to the alternating group, no matter what x is, or no matter what little a is. So for all elements of your symmetric group, Sn, and little a, so any element of your alternating group. So we need to show this in general. So the strategy for the proof is to take this and find whether it has an odd or an even number of cross points, right? And so if it has an even number of cross points, then it's an even permutation. And proving that we also did in chapter 12. So go back. All right. So let's find n of this. How many cross points does this have? And if the answer is even, then we know that this resulting permutation, so x inverse, it's just that's just a permutation. A is permutation, X permutation. So this resulting permutation here, if it's even, then we know it belongs to the alternating group. So let's try to prove that this permutation here, this resulting permutation, is even. All right. So so we can use this theorem here, 41. Here it is here. So we're now plugging in this x inverse AX here into our n. Right. Now we can split this up using this theorem into these three parts. Right. Well, here we've just split up two, but we can apply this kind of reasoning twice. So if we had x, y, z, we could have x here and then y, z here, and then we could split that up, y, z, into n, y, and n, z. Right? So we can do as many times as you like. So here we've done it like 3 times, so we now have 3 terms. Okay? So n of x inverse plus n of a plus n of x. Now, here's something a little new. Did we? Maybe we did. In proving that this was a group, subgroup. Can you see? Now think about it a little. Can you see that the number of cross points for the inverse is the same as for your original permutation? So the number of cross points for x just any permutation. Can you see that the number of points of x will be the same as the number of points for the inverse of x? Is that intuitively obvious to you or not? If not, consider this. Well, I'm trying to show you that the number of cross points for the inverse is the same as your x. Going this way. That's your permutation x, right? And let's say this object gets moved to here and this object gets moved to here, and here's a cross point. Okay? Now if you go the other way, when you go like up in a sense, so you're starting here and you end up with this, there'll be the same number of cross points, right? Like if you go down in a sense, if you go from this arrangement to this arrangement, then let's say you get a cross point here between these two pairs. But if you go back up, you're going from these two to these two. Same number of cross points. Right? So